we have half hour, and I'm going to discuss the complex number, namely the properties of complex numbers and complex solutions of the equation. The first part, and second, I'm going to explain what does mean a complex solution of linear system and what does mean a complex vector space. I'm going to recall maybe well-known notions, and I am going to recall what does mean complex numbers. And natural way to appearance for a complex number is a series of solutions of equation. I recall if we have some simple equation x plus a is equal b, let's suppose that a and b be a natural number. Such solution, generally speaking, has not a solution. For example, x plus 2 is equal 0. This solution, this equation has no natural solution, but this equation has the integer solution, and this solution x is equal minus 2. And if we have only natural numbers, we can't to solve this equation, the equation of type x plus a is equal b in natural numbers. But if we extend the set of numbers and include negative numbers, negative integer numbers, we obtain that in any cases such equation has solution, and we extend the set of natural number and obtain the integer numbers. But if we consider the equation of such type a times x is equal b, where a and b be integer, this equation in some cases also has no solution. For example, to x is equal 1. This equation has no solution. But next step, we must to extend this numbers system, and on this way we obtain so-called rational numbers, and so on. The last step, we obtain the real numbers. Field. What does mean field? In the field, if we have two elements a and unit, such equation has a solution, and element x is inverse element for the a. But we must exclude the case when a is equal 0. For any non-zero element, such equation has the solution. What does mean the number system? I suggest when we tell about number system, we mean that we have some set which do operation addition and multiplication, and abstract generalization of such number system is so-called ring with an abstract set with two operation with two operations, addition and multiplication. And this operation satisfies some axiom: addition associative, commutative. This is the same operation for the first operation of the vector space. And other operation multiplication, which operation associative and in many cases also commutative. And we have also axiom of distributivity, multiplication, relatively addition. And in these cases we obtain the so-called ring. As a rule, commutative ring with unity. Unity, the element which product of this element and any element is equal this any element. The examples of ring is a ring of integers. If rings such that any non-zero element has the inverse element, other words, such equation has a solution if A be a non-zero element. Such ring is called field, and we have two examples of field, Q and R. If we consider the real numbers, and we can see that some equation, for example, x squared plus 1 is equal 0, have no solution. For example, such equation hasn't solution. And natural question: can we extend the real numbers, the set of real numbers, such that, for example, such equation can be has solution? And more generally, maybe any algebraic equation will has solution. And the answer on this question is yes. We can we can extend the real numbers such way that we obtain the more general set, more wide set, complex numbers which give solution of such equation, and more generally give the solution of arbitrary algebraic equation. What does mean a complex number? The natural way to define a complex number consider the set of the pair of real numbers. Complex numbers, Z, by definition, is a pair of real numbers, A, B, D, real numbers. And if we can consider the set of complex number as a vector space, which isomorphic arithmetical space, arithmetical vector space R2. And this, so we have natural operation of addition if we have two complex number. Naturally defined addition of complex number as addition of corresponding vectors, namely, A1 plus A2, B1 plus B2. And we have also a geometrical interpretation of complex numbers as a vector on the plane. Complex number can be considered as a plane vectors, and its component A and B be the coordinates of this vectors, of this vector. But we can to define also multiplication on the set of this pair. Namely, if we have two pairs A, B, and C, D, we can define multiplication by the following formula. The first element of the pair of product is equal A C minus BD, and the second element is equal A D plus BC. What's the idea of such definition? I know that complex number forms the vector space of a real number. And we have also defined operation, multiplication operation. If we have a real number lambda and pair AB, we obtain that this product is equal lambda A, lambda B. And easy to see, if the first multiplier is equal A0, we obtain exactly product on the real number A, AC, AD. So we can identify the real numbers with the pairs A0. For instance, the unit 0 is a simple real number 1. Let's denote by I the pair 0, 1, 0, 1, image unit. And we obtain the natural basis in the set of pair with basis first element 1 and second element I. 1 is equal 1, 0, I is equal 0, 1. And any complex number can be presented as a linear combination of these basis vectors A plus BI, where A and B be real numbers. The next remark, if we use this formula and multiply 0, 1 on 0, 1 in correspondence with formula, we obtain minus 1, 0, minus 1, 0. So we obtain that square of image unit E square is equal minus 1. And this property is uniquely defined this operation of multiplication. Easy to see, if we suggest that complex number satisfy the axiom of the ring, we obtain that this definition of multiplication is it follows from this general axiom. Namely, let's suppose that pair AB A plus bi, CD is a pair is equal C plus dy, and let's multiply first number on the second. Using operation of distribution axiom, we can obtain that this sum is equal A times C plus di plus bi times C plus di. Using distributivity law, we obtain AC plus ADI plus BCI plus BDI square. Using that fact, this I square is equal minus 1, we obtain the following equality: AC minus BD plus AD plus BC times I. And we obtain the pair AC minus BD, AD plus BC. So we obtain that this law of multiplication is equivalent to the condition that the square of image unit is equal minus 1. So we obtain the set of new numbers, which we call complex numbers, and on these numbers is defined operation of addition and multiplication. Moreover, any complex number is invertible. Any non-zero complex number is invertible. It's a simple observation. If we have some complex number z, which is equal a plus bi, a is called real part and b image part of the complex number. We can correspond these numbers so-called z bar complex number. It's called adjoint, and this complex number, the real part is equal real part of a, but image part has opposite sign, and easy to see that product of z bar, easy to see, is equal a square plus b square, and greater or equal 0, and equal 0 only in the case when a and b both are equal 0. Easy to see if this observation help us to find such element z inverse element z minus up minus 1, such that the product z and inverse element is equal unit. Because z bar is equal real number a square plus b square, we can define inverse element as the ratio z bar divided the product z bar divided on these real numbers. And we can see that this product is equal z bar and is equal unit. For example, if z is equal unit plus I, z bar is equal unit minus 1, z bar is equal 2, and if we obtain that inverse element is equal unit minus I divided 2, and if we multiply, if I multiply is to see that I obtain that this product is equal to. So we can to add, multiply complex number and to solve the some simple linear equation. If we have some linear equation and we can multiply numbers, divide one numbers on 2 and add numbers, we can use House elimination method and to solve the arbitrary linear system. It's enough. But if we have algebraic equation, we must to find root of some degree from the complex numbers. For example, we can to solve such equation. Z cube is equal 1. From this fact, we must to find the root of third degree from unit. We can. I need maybe 5 minutes to finish my explanation. Okay, I maybe more simple. I sent notes with explanation of this operation, and if you have any question, we can discuss your question on the consultation. But on this example, I try to explain in general way how to solve such general equation. We have Zn and A will be arbitrary complex numbers. If you have complex number Z, I know that this product Z and Z bar is a positive real number, and I can denote by model Z root square of this product Z bar. Geometrical explanation: the model Z is the length of the vectors which present our complex number, and any complex number can be presented in the form easy to see that square of this element and this is equal unit, and I can present this element cosine and sine some angle phi, which uniquely defined by these numbers. We have unique solution of the following system. Oh, why not unique? Unique up to numbers which is a product integer and to p. And we can present this complex number in the following form: cosine phi plus sine phi. And the main idea, if we have two complex numbers z1 and z2 and present this number in this form, and multiply these two complex numbers, the result of this multiplication is a complex number which has the model, which is a product of the models, and phi, which is called angle or argument of the complex number, is the sum of this argument of multipliers. We obtain the following nice formula for product of the two complex numbers. And from this formula, easy consequence that if we have complex number z, the n power of this complex number can be calculated by the following formula. The model of this complex number is n powers of the model initial complex number, and argument is a product n and argument of initial complex number. It's a very nice formula, help us to solve this algebraic equation. We can present z in the such trigonometrical form as z cosine phi plus I sine phi. And the right side we can present as a model A cosine psi plus I sine psi. But as I remarked above, the argument defined up to some product 2p on some integer k. And we obtain the following equality. After them, easy to see, we can rewrite left side in the following form, and we obtain two simple equations for the model and argument. Easy to see that the model z is arithmetical root from A, is uniquely defined real numbers, And argument phi is defined by the following formula: psi plus 2pk divided n. And for the values k is equal 0, 1, and n minus 1, we obtain the different values from the complex number z. We obtain n solution z0. And so on. We obtain zk solution. And this solution, the values from the values k, when k goes 0, 1, and so n minus 1. And using this formula, we can to solve some algebraic equation. But more precisely, we can to solve equation of the such type. And if we can to reduce the arbitrary equation to the equation of such type, we also can to solve this equation. Okay, I have no time, and I must finish my introduction. And, I hope that my notes to help to prepare the exam. And we must to solve some simple equation. For example, EZ plus EZ1 plus 1 plus EZ2, for example, is equal 0. For example, you can solve such a simple equation. What does it mean, solve this equation? We can to express Z1 as minus Z2. And we can present this this ratio as a complex number, and we can multiply denominator minus I and 1 plus I, also multiply minus I, and the product, the I minus I is equal 1, and this minus and this minus subtract and keep one other, and we obtain I minus 1 Z2. So Z1 is equal minus 1 plus E times Z2. And we obtain the solution of this equation. We express Z1 in terms Z2. Z2 is free variables, and Z1 is dependent variables. And we can put the free variables any complex number and obtain the value for the second numbers. And we can find the basis. For example, we can put Z2 is equal 1 and minus 1 plus E be the first component of these vectors. And we obtain that the space solution, the linear span of the set of such vectors with coordinates. And we obtain the space of solution as a linear span of this system, which contains only one vector. Thank you for your attention. Maybe a question about complex number. I hope that you know this area and can use to solve some complex equation.
Professor, I have a question about the exam program.
Yeah.
Last semester you sent us like 45 exam questions. And this semester we only sent 16 theoretical questions.
Yeah.
You will send or we will don't have?
Yeah. Exam will contain this theoretical question, yeah. And all of these theoretical questions will be done in the lecture notes, yeah. I will send this.
And exercises we solve like in a seminar, we will have, right?
The last sem, which connect with complex number, we didn't solve the sum problem, but we have consultation before exam, and I sent the example of exam problem. If you will have a question, we can organize some consultation, contemporary consultation, and discuss this problem. Yes. Any question will be done in the list of the standard exam question. Yes, and this list will be contained the solution of such complex equation. Is one of the examples. Yes. Maybe any questions? Other questions? Okay, thank you for attention, and I hope that during maybe 2-3 days, I send full list of the exam standard problem and send the last lecture. Thank you.